Hello. So what kind of force is required to produce a projectile motion? A constant downward force of mg, right? Because then the motion will have a constant downward acceleration of 9.81 meter per second squared. What about a circular motion? What kind of force is required to produce circular motion? Well, we need a centripetal force whose magnitude is mv squared over r. Because then the motion will have a centripetal acceleration of v squared over r. So what about simple harmonic motion? What kind of force is required to produce SHM? We already know the acceleration of SHM is a is equals to negative omega squared x. We can multiply m to both sides of the equation. So what is the mass of a body multiplied by its own acceleration? It's the net force experienced by the body, right? So there we have it. To produce SHM, we need a net force that's given by negative m omega squared x. So just like the acceleration, the net force for SHM is directly proportional to displacement and is always directed towards the equilibrium position. So it's a net force that always tries to pull you back to your equilibrium position. Because of that, we often call it the restoring force. Okay, you have seen this motion before. I've told you that it's actually a SHM. So now let's think about the forces that make it a SHM. So first of all, when the mass is at its equilibrium position, the two springs are equally stretched. So the leftward tension force and the rightward tension force cancel each other out. That's why this is the equilibrium position, where the net force is zero. And whenever you're displaced to the left, the spring on the right is more stretched than the spring on the left. So the rightward tension is stronger than the leftward tension, which means the net force is rightward. So you have a restoring force pulling you towards the equilibrium position. On the other hand, whenever you are displaced to the right, then the leftward tension force will be stronger than the rightward tension force. So the net force is leftward. So again, you have a restoring force trying to pull you back towards the equilibrium position. And that's why this mass here has got to oscillate because of the restoring force. Now, is this restoring force directly proportional to displacement? If the two springs obey Hooke's laws, then yes, right? Because then the tension forces will be directly proportional to displacement, and therefore the net force, the restoring force, will also be directly proportional to displacement. So yes, this is a SHM. Okay, now let's look at the motion from the point when it goes from the equilibrium position to the extreme right position. So we're talking about this motion here, yeah? So what just happened was that the mass, as it travels from here to here, it experiences a larger and larger restoring force. So it slows down at increasing rate until eventually it comes to a rest at the extreme position here. So it's at rest now. Does it stay at rest here? Of course not, yeah? Look at the springs, man. In fact, this is the point where you are experiencing the strongest restoring force. Because of that, you accelerate back towards the equilibrium position. You'll be speeding up as you do so, but you'll be speeding up at decreasing rate because the restoring force also gets weaker and weaker. So now you have arrived at the equilibrium position, and the net force is now zero. Do you stay there? Of course not, yeah, because you arrived here with a certain velocity. In fact, you arrive here at the maximum speed of the oscillation. So your inertia, your momentum will carry you over, and therefore you swing to the other side. But you slow down at increasing rate, comes to a rest here, and then speeds up towards the equilibrium position at decreasing rate, and then overshoot, and this repeats forever and forever. So the life of a SHM is really quite sad, huh? You just keep doing this repetitive motion forever, simply because the restoring force keeps pulling you back towards the equilibrium position, but it does not leave you there. You're always overshooting the equilibrium position. So you slow down at increasing rate, speed up at decreasing rate, slow down at increasing rate, speed up at decreasing rate, and so on forever and ever. Alright, that's all. Ta-ta!